Welcome to this 101 series session. My name is Frank Amankwa. I'm going to take you through into software development, a little bit about myself. I currently work as a software development manager in a company in the UK called GameSys. We build online games, online casino games, bingo games, slot games, and that type of thing. In my spare time, I run a number of online communities, one of them being a software development community, and that's how Doris has reached out to me to do this session for you tonight. My Twitter handle is on screen. It's Agile Frankie. If you want to get in touch, it's the best way to reach me. Okay, so without further ado, I'll jump straight in. So what are we going to do today? I'll skip the introduction bit. I've introduced myself, but this is online, so I won't ask everybody to introduce themselves. So we're going to cover quite a few things in this session. We're going to start with a high-level software development overview, a little bit of history. Then we'll talk about, discovering requirements and the different ways in which you can discover requirements for software development. Then we'll look at programming languages, the different types of programming languages, how you actually select a programming language. And then once you've selected that programming language, the sort of things that you go through during software development. Then we'll briefly talk about software testing, and then we'll wrap up looking at how, if you're not already doing software development, how you can start. Okay, so a little bit of history. Somewhere in 1970, there was an academic called Winston Royce, and he wrote a paper and presented at a conference, or a software conference. And basically the summary of his paper was that how software was being built back in those days meant that it was quite inefficient, a process. And he described the process as a sequence of steps that you take from when you decide that you want to build some software to when you actually build the software. And these sequence of steps he described as a waterfall. In his presentation paper, he was trying to say that this isn't the way that you build software, or this is the best way to build software. But the people who were present didn't take any notice. They liked the idea of the waterfall, and that's how the term waterfall development was originated. Winston Royce didn't actually call it waterfall, but the diagram he drew looked something like this. So it was a sequence of steps starting from requirements to design, to implementation, to verification, to maintenance, which is when the software is actually live and being used by users. Fast forward a few years, 40 years plus, today, the waterfall approach to software development is still used in quite a lot of different industries. It is not bad per se, but a lot of software projects that were using this approach back, over the years were failing. And before I came to understand why that was, I kept asking myself, how can the software project fail? You get given a set of requirements, you code those requirements, you give it to your customer. How can that be difficult? Then I came to learn that, failure doesn't mean that you built the thing wrongly. Failure also means that you built the wrong thing, right? So, for example, if it takes you 2 years to build software, the requirement 2 years ago might have changed by the time the software is finished. If the business problem you try to solve no longer exists, then even though you've built the software according to how the customer asked you to build it, it's of no use to the customer. So technically, that's a failed project. So that's the sort of thing that was happening over the years since the 1970 paper that Winston wrote. So this is, if you want to look at it from another angle, waterfall development is a sequence of one-off activities. You start off the project with analysis. It might take you a few weeks, a few months. Out of that process comes a pile of paper. Then you do some design, which is from the analysis. That is also some more paper, more drawings, more artifacts, whatever. Even if you're using a computer program, you're still not writing any code. After the first two phases, then the designs get given to software developers who would write the code to meet the design. Then they would pass it on to software testers. By the time you get to the fourth stage, you're probably running out of time. So what happens is a lot of corners get cut at the testing stage, and the software is released without being fully tested. That happens a lot, even today. Some of the projects I work on, this still happens. We spend a lot of time up front doing things, then when it gets to the end, there's no time. We want to go live, and we just cut corners with testing. So in a nutshell, this is how waterfall development looks. Then around 2001, a bunch of software experts got together and came up with this process that they refer to as Agile. And basically, Agile has various, definitions and descriptions, but I just look at it as the waterfall approach flipped on its head. So in this picture here, you can see that I flipped the diagram over on its side, and I've also rearranged some of the layers, right? So if we look at the diagram on the right, the activities are continuous, right? Rather than doing one-off big chunks, you do small chunks of each of those one-off chunks in each iteration. So time moves across the x-axis, and as you go along, you're building full parts of the software. So every iteration, you're actually building something that the customer can test. So when you're halfway through an Agile project, you've actually built about half of the functionality that's required. Whereas when you're halfway through a traditional project, you haven't written any code yet. You've just finished design. So that's the main difference between traditional software development and what has become quite popular today and we refer to as Agile software development. Another way to look at Agile software development is a sequence of cycles, right? So software, even in traditional software development, is built in cycles. The main difference between traditional development and Agile is that in a traditional software project, the cycle is very long, right? The cycle could be about 2 years or 3 years, depending on how complex the project is. Whereas in an Agile project, there are many small cycles. The cycles consist of the same steps, but you do them many, many, many times. What that gives you on the customer is many opportunities to assess what you're building and for the customer to change their mind. In a traditional project, the customer can never change their mind. Once it's signed off, until it's built, the customer doesn't even know what they're going to get. Whereas in an Agile project, every 2 weeks or every week or every month, the customer can look at what you've built and decide whether they want to carry on or not. So before you spend all the money, they can actually see what they're getting for their money. So like I said, all software development is cyclical, right? You always go through analysis, design, implementation, testing, evolution or release or maintenance. All software development goes in this cycle, and this is what you refer to as the software development life cycle, or the SDLC. So you will realize that the SDLC refers to both the traditional approach and also the new Agile approach. They're all SDLCs, they just have different characteristics. So with that out of the way, let's look at how you discover requirements, because on every project, even on non-software projects, it all starts with somebody's idea, right? It all starts with somebody's problem or somebody's requirement. But before we jump into it, I'd like to debunk 3 myths about discovering of requirements. And you realize I use the word discovery, not gathering.
Frank.
The reason I picked the word discovery is, the requirements are not there to be gathered, right? Usually you don't know what you're building, right? You spend time talking to your users, and over time and various conversations, you find out what you're building. So it's a discovery. You don't gather. If you say gather, it's as if it's the leaves on the floor that you pick, right? Requirements are not like leaves on the ground. They actually evolve and emerge as the project progresses. So the first myth, or the first fact, is that it's impossible to gather all requirements at the beginning of a project. This has been proven many times, and this is contrary to the traditional approach where you do all your requirements analysis at the beginning, right? It is impossible. The reason it's impossible is you don't know all the requirements, right? And even what you know will change. The second thing is that whatever requirements you do gather are guaranteed to change. So if you're 100% sure that what you're going to gather is going to change, why bother gathering all of it up front? Why don't you delay gathering it? So when you actually discover it, it's closer to the truth. And then the last thing is that there will always be more to do than time and money will allow. What does that mean? There's always going to be more requirements. There's always going to be more features. So you should just focus on the most important features at any point in time. So if we look at traditional requirement discovery, it usually starts off with a feasibility study. Somebody says, I want to build this. They'll commission a short feasibility study. Out of that will come a feasibility report, right? And that tells the person who's going to pay whether this project is feasible or not. If the feasibility report is approved, then the project moves into a requirements phase where business analysts will spend time and gather various requirements for the project.
Frank, let's break it.
Out of the requirements analysis phase will usually come a systems model and also a requirements definition. That requirements definition and the systems model will get put together in a requirements document, which is the box at the bottom here. Anything with a red outline is an artifact that comes at the end of a process. So now you have a requirements document that will get used to generate a requirement specification. And this is what will get passed to systems designers or systems architects for them to actually use to design the system that's being built. Then about 2 decades ago, a process was introduced by 3 gentlemen called the Three Amigos. I'm trying to remember their names. Can't remember the names off my head, but they came up with this process called use case analysis. And basically, use case analysis made it easier to capture requirements without having to write lots of documents. So a simple use case consists of a customer, and the oval shapes signify the things the customer wants to do with the system. If you compare this to the traditional approach, you realize that this is a very simple way of looking at it. Obviously, use case diagrams can be quite complicated, but this is a very simple example. So there's another way of gathering user requirements. Usually you'd write use cases and then you write a short document to describe each use case. So for instance, subscribe to reviews is a use case. On here is represented by just one oval, but then once you've agreed this is what you're going to build, you will take that and then write a brief description of that use case. Then around late 90s, early 2000s, when the Agile movement was sort of taking shape, another approach was introduced called Agile Requirements Discovery and the use of user stories. So user stories represent a user's need, right? It allows for a requirement to be captured in 1 sentence or 2. What user stories are used for are they're like a placeholder and a promise for a discussion later on. Then features are usually capabilities that a product owner is interested in, something that provides value to users, and they are normally realized by a number of user stories being completed. And then an epic, which is the topmost layer, usually is a large initiative that might comprise a lot of features and a lot of user stories. So these 3 levels were introduced around the time when Agile was becoming popular, and it's also another way of gathering user requirements. So as you say, there's 3 ways of gathering requirements. There's a traditional way that's very structured. So for instance, for example, if you're building software to power a Boeing 747 aircraft, right? You probably have to be quite rigid because the airline industry has a lot of rules and regulations, and obviously you're dealing with customer safety, right? So you wouldn't want to cut any corners. You probably want to be very, very, very rigid. If you are building a social network like Facebook, I mean, if there's a bug or something goes wrong, nobody's going to die. right? So you would, you could use an approach like use user stories, or you could use use cases, if that's what you want to do. So there isn't a one size fits all approach to gathering requirements. You have to pick the right approach for the job. So if you compare them, traditional versus agile requirements, you will realize that in the traditional requirements, the level of detail is quite high, right? And the level of specification, i.e. the fine-grainedness is quite high. You write a lot of requirements, you got a lot of detail, but as you go down the list to use cases, the level of detail is about medium size. And then user stories, there's very little detail, because user stories are encouraging you to have a discussion close to the time you're actually going to build the software. So that sort of brings us to the end of the Agile requirement discovery session. So I'll move on to the next session, which is about software design.
I think your slides aren't moving.
So a traditional software design process is similar to the software requirements analysis process. It is quite structured. So the input usually is the output of the traditional software requirements process, which is the requirement specification. Into that, that goes into what you call the architectural design and the abstract specification process. The output of those two processes is a system architecture and a software specification. So let me just check, make sure I'm not getting any messages. What slides are you seeing now? Okay, hold on a sec. Somebody says my slides are static. I'm on the software design process slide.
Yeah, can you make your slide? Can you make it full screen at least, so when you move? Frank.
I can't hear you. That's a bit funny. Okay, that's, at least you can hear me. That's good. Okay, so can you see the software design process slide? Great. Okay, great. So let me continue. Keep pinging me every now and then. I'll come back here to make sure you're following me. Great. Okay, great. So let me.
Can you show your slides in full screen?
And how is the speed? Am I going too fast, too slow, or is it okay? Okay, great. Let's carry on. Okay, great. So as I was saying, the output of the requirements analysis is this requirement specification, and that goes into the architectural design phase. Out of the architectural design phase, the next phase is abstract specification creation. Each of these phases creates or ends up with an artifact. So the first phase is a systems architecture, the second phase is a software specification, and so on and so forth, right? At the end of the design phase, you have the algorithm design, which is the last process, and out of that comes what you would refer to as an algorithm specification. So this is what a programmer or a bunch of programmers will then take and write code in whatever language, Java, COBOL, Fortran, whatever, to actually build your software for you. So the design process is a number of sequential activities, each which spits out an artifact, right? Usually some diagrams or some paper on which some designs have been created. Okay. Feel free to post questions in the chat, and then I'll come through them, and then we can answer them. So this is a traditional software design process. Software design, the steps haven't really changed over time, but rather than going through them in this rigid fashion, if you remember the agile slide that I showed you before, you would only do this for a very small portion of the software, right? So in each iteration, the features that you decide that you're going to build, you would go through this process for just those features. You would never go through this for the whole project, because that could take you months, right? So you do just enough design for the features you selected for the iteration. At the end of that iteration, you get those features reviewed. If your customer is happy, you pick the next set of features and you go through the whole process again. So the whole software development cycle hasn't changed. It is the quantity of work or the quantity of features that you do per cycle that has changed. So the length of a typical cycle has shrunk from, let's say, a year or 2 years to 2 weeks, right? So every 2 weeks you deliver something small and then you start again. That gives you multiple chances to improve and for the customer to potentially be able to change their mind if what you're building is not what they're looking for. Okay, so jumping right ahead, there's like in every engineering profession, you have blueprints, right? So if you look at how civil engineering works, right, you know, there have been many bridges built over the years, right? So every time you're building a new bridge, you don't reinvent the wheel. There's potentially some patterns that you'd use. You know, if you're building a bridge that a railway train goes over, you build it using an arc. If you're building a bridge that goes over a river, you build it using some, you know, some things that let the bridge hang in the air. Those are all patterns that have been refined over time. Same way in software engineering, there's a number of patterns that have become commonly used. And usually a pattern is just an approach to solving a problem that people have repeated and used over time. Is become something that's de facto. This is a popular list of patterns. They're called the Gang of Four patterns. They were designed by 4 software engineers. They're broken into 3 groups. The 3 groups are structural patterns, creational patterns, and behavioral patterns. So the patterns that have the orange background are the structural ones, right? So even their names signify that, right? So for instance, an adapter is a structural pattern, the bridge pattern, the composite, the decorator, the facade, the flyaway, and the proxy. They're all structural patterns. They help you give structure to your software artifacts or to your software program. Then the creational patterns you use when you're creating new objects or new instances of objects in your software. So things like the factory, the builder, the prototype, and the singleton. Those are all creational methods. Anytime you hear them being used, it means something is being created, right? Then the behavioral ones normally capture some behavior, right? So for instance, if you've written any programming, you will realize that if you have a collection of items, you have to loop through them, right? And the action of looping through them is called iteration. So the iterator pattern, every programming language has that pattern built in because every programming language supports creating a list of items that you can actually loop through, right? So design patterns is a skill that every software engineer must learn over time. You don't have to sit there one night and chew and pour, right? It's something that will come with time, but you should be aware of what patterns are out there. And as you progress in your journey of mastering software development, those will become second nature. It's like a language. You won't have to say I'm using a command pattern. You just use it because you know that's how to solve that particular problem. It's an area that a lot of people find difficult, but I always say look at it like a language. Start with the easy bits. And then as you go and as you use them, you pick other ones and learn them as you progress. Okay, so that's that. So that's the end of the software design section. The next thing I'm going to cover is programming languages, and obviously this is a software development session, so we're going to get to this at some point. So I'll start by going over what we refer to as the generations of programming languages. So it started off quite earlier on in computing with what we call machine language or first generation languages. These were languages and are still languages that were used to program the hardware, right? So these languages were quite low level. They were quite tedious and quite error prone. You know, if you remember, I mean, we're all probably too young to remember, but when people had to use punch cards to write programs and then hand it to an operator to input into a machine, that is where, you know, machine language was being used. Companies who write operating systems or device drivers still have to write this sort of, you know, code. I mean, there's different languages that you can write and compile into machine language, but generally anybody who deals with hardware has to have an appreciation of some low-level languages. Then came the next generation, which was usually specific to a particular processor. So let's say a company like IBM or Sun Microsystems builds a processor, they would normally build a language to go with that processor. So then when companies wanted to write software, like operating systems to run on that processor, they'd have to use an assembly language as part of the building process. Then the third generation, which, you know, a lot of us use these days, were the third generation languages. These were usually independent of a particular hardware platform because the assembly language took care of that. So the third generation languages actually run on top of operating systems and environments that are built using assembly languages. So languages that we know today, like, you know, C, C++, Java, Perl, Python, Ruby, these are all third generation languages. They normally run on a number of hardware platforms, run on a number of operating systems. Some of them are statically typed, so you have to compile them. Some of them are dynamically typed. They just get interpreted and run, you know, as you read them. So there's more languages in the third GL space than there were in the first and second GL space. Then there was also a fourth generation language group, which was supposed to be closer to human natural language. It didn't quite take off back in the day, but as you can all attest, things like, you know, AI and machine learning are becoming quite ubiquitous now, and natural language processing, things like Alexa, the Amazon, you know, language processing engine, are becoming common now, right? So even though it says here that natural language was ambiguous for computers to understand, that is changing, right? With AI, with Alexa, with Siri, you know, things like Siri on your iPhone, it means that this problem is actually being solved quicker than a few years ago. So these are the four generation languages. Most of the languages you will learn and use will be in the third generation space. Fourth generation languages are making a comeback as well. Yes, okay. Okay, so you're still design patterns. Wow, okay. I wonder what's happening there. So let's see. Design patterns were 2 slides ago. Okay. Can you see the programming languages slide? I think I should leave this open so I can see what you're typing, because I don't want to lose you. Okay, can you see the software generation slide? Okay, and then can you see, okay, fine. So this is where I was, right? Okay. Do you mind if I leave the screen open so I can see the chat and you can see my slides? Yeah. Okay, great. So let's carry on, right? So like I said, so these are the 4 generations of languages, and natural language is becoming mainstream with things like Alexa, with the likes of Siri on the iPhone, and there's a lot of competition in that space, right? You know, machine learning, deep learning, you know, there's a whole lot of AI happening. Things like, you know, autonomous cars, and you know, there's a lot of stuff happening in the 4GL space. So the next slide is a tag cloud of programming languages. Can you see that? So this slide has a great, okay, so it has, you know, I'm sure you recognize some of the languages on this slide. The point I'm trying to make here is that there's a lot of languages to choose from, right? So if you're not programming already and you want to learn a new language, where do you start? It's a question I get asked a lot. And my answer to that question usually is, all languages have things in common, right? Every single language, whether it's Java, whether it's C++, they have things in common. And those things are data types, operators, loops, conditionals, functions, and exceptions. So data types refer to the types of information that can be processed by a programming language. I mean, most data types are numbers, strings, booleans, and collections, right? You know, all languages support those basic data types. Operators are actions that you can actually take on data types. So for instance, the numbers, you can add them, you can subtract them, you can multiply them, you can divide them. Strings, you can concatenate them, you know, you can do stuff. So those are the operators. Normally operators operate on data types, right? Loops speak for themselves, you know, iteration, like I spoke about before. Conditionals, if-else statements, functions, groups of statements, exceptions when things go wrong. Every language has these features. So if you were going to pick a language, right, it doesn't really matter which language you pick. You will have to learn these features. So usually I say, look, pick the easiest language to learn. It doesn't matter what it is. People say it's Python, right? Fine. Some people say it's Java. I don't really mind. Pick the easiest one for you, and then try and master these common language features by writing some example code and, you know, playing around and solving some simple problems. If you go onto GitHub, there's plenty repositories with sample programs, and, you know, you can do coding katas and that kind of thing, right? Once you're comfortable with the common language features, then the next question you ask yourself is, hold on, next question you ask yourself is, what problem are you trying to solve? So once you learn the language, the next thing is you need to pick a language then that's best suited to the problem you're trying to solve. So for instance, typical problem areas could be, you know, you might want to write an online game, right? A simple online game, or you might want to write, you might want to develop an app, right? A mobile app, or you might want to build a website, right? Or you might want to, write, a program that passes some XML file and does something fancy. Whatever the problem is, there is a programming language that is more suited to that problem. Once you've figured out what's suited to your problem, you also want to make sure the programming language you pick is widely available, i.e., there is a big community out there that's using a language, so that if you get stuck, you can Google or you can join a community group and get somebody to answer your question, right? The same thing applies to it being widely used. Ensure that it's used by more than just a small community of developers. make sure it's probably used in industry, because ultimately you might want to get a job, right? So there's no point in learning some niche, programming language that might have a big community, but no company is hiring for, right? So you also need to check the job boards to see which programming languages are in vogue, right? Because if you're going to spend time learning something new, you might as well learn something that you can actually find a job with, right? So the three main areas that usually come up when people are choosing programming languages are as follows. These are what we refer to as dynamic languages, and these are usually used in the web space, right? So when people are developing dynamic websites and applications, web plugins and widgets, web-based games, Ruby, Python, JavaScript, PHP usually come to mind. There's others, but these are the four most popular ones. Then Ruby and Python also get used quite a bit in the sysadmin space for writing scripts that automate common programming tasks. Python is supposed to be the popular choice for learning programming because its syntax is quite simple, and with one line of code you can write a hello world application. Whereas some other languages like Java, hello world is about 6 or 7 lines of code. As you can see, each of these has an online community. If Meetup is big where you are, then if you go on Meetup, you find that each of these has big Meetup groups. But if you're not, then obviously you can join online communities and post your questions, see questions people are posting, and then learn from the community that way. Obviously, Google hosts a lot of communities. Google is quite active in the JavaScript space. They've got their own JavaScript framework called AngularJS. I'm sure there's a big community out there. Facebook have their own JavaScript framework called React, so they have a big community. So there's always a community around all the popular languages, and they should be your first port of call if you'd like to learn that language. On this slide here, I would recommend definitely looking at JavaScript, because JavaScript as a web is the only language that runs in a browser, which is quite unique. And it has made a very big comeback, right? JavaScript used to be just this language for using to add simple animation to websites. Now it has become a serious language that everybody is learning, and a lot of things are happening in the space. If you want a quick, start, then maybe Python might be a good one to start with. Python is also quite popular in the data science community. So anybody doing machine learning or artificial intelligence or data science in general, Python seems to be the language of choice. So if I had to pick 2 out of these 4, I'd say JavaScript if you're heavy on the web, on the web development side, Python if you want to go down the data science route. Either of them is a good choice to start learning programming, but those are the paths they'll take you down if you decided to go that way. Then the next group I call the static Java-like languages. Java is probably the oldest one of the 3. Java was created in the early to mid-90s by a bunch of guys at Sun Microsystems. Then C# was created by Microsoft in the early 2000s. And then Android was created by Google. Android uses a Java language, but has its own compiler. But if you're a Java programmer, you can program Android as well. Java was created originally for creating little applets to add dynamic functionality to websites. It's matured to become the de facto language for developing backend platforms. The UI library for Java didn't really take off, so you find very few applications have a Java front end, right? But Java has become a very ubiquitous backend language. Whereas C#, because it's a Microsoft tool, has become the de facto for building rich, maybe desktop-based clients. You can also use it to build web-based clients. In banking, they use C# a lot. and it's usually used to build rich web-based clients. And obviously, as we all know, Android is used for building apps and mobile games on the Android platform. So the problem domains these languages usually cover are client-server applications and APIs, that's Java and C#, and then mobile application and games for Android. Then the third group of languages I call the hardcore languages. So these are the C family of languages. C is the oldest of them. C++ came a few years later when they wanted to add object orientation to the C language. And Objective-C was introduced by Apple when it started its iOS products. They're all based on the C language, so they're quite low level. You need to know, how to do things like memory management and that kind of thing. So it's quite low level programming. It's not for the faint-hearted. It doesn't mean it's difficult, but you have to learn a bit more to get good at it. They're usually used for building high performance applications like banking applications, trading applications, that kind of thing. Things like complex computations, things that will get done in the European Space Agency, or things that will get done in like a high computation system, will usually use C. The reason for that is that it works closer to the hardware, right? Languages like Java have a runtime between your application and the hardware, so there is a bit of a delay for certain activities, whereas languages like C compile to machine or to very low level code, so they interact quite well with the hardware. So things like embedded systems, things like in-car systems, things like systems that operate jet fighters and aeroplanes and that type of thing are all written using low level languages, potentially C, C++, or other low level languages. Recently, the C++ has been used a lot in computer and console games. And also, Objective-C is also used quite a lot in mobile applications and also games for the iPhone and the Android, iPhone and the iPad. Like the languages before these, they all have big communities that you can actually join and learn from. But like I said, they're a bit more involved, so the learning curve for this group of languages is quite high. I've listed them in order of difficulty to learn. So if you're just starting out, your best place to start with one of these four. Python or JavaScript, potentially the best two to start with. If you want to build, client-server platforms, you want to expose APIs, you want to build mobile games and mobile apps, then Java, Android, C# are a good place to look. These first four are dynamically typed languages. It means that they're not compiled, so they're the way you write the language is exactly how the language runs when you run it. Whereas Java, C#, Android, and also the C++ languages are compiled. So when you write the language, it's converted into another format before it actually runs on the computer. That sort of summarizes the three categories. There's way more languages than I've covered here, but these are the three categories that you normally will find people learning when they're starting out. So that brings me to a natural break in the session. Do you guys want to ask some questions, or should we go to the end and ask questions at the end? Okay, so no questions. Let's carry on then. So that's it for software development. I'm going to quickly talk about software testing. Okay, give it a second. Okay, fine. So let's give it a second, see if people have some questions.
Yeah, I think it's fine. You can go on.
Okay, thanks, John, and thanks, Andrew. Okay, so let's quickly look at software testing then. So that was software development, a very high-level whirlwind tour. So software testing is, if you remember the diagram I showed at the beginning, is usually referred to as the last phase of the software development cycle. It doesn't have to happen only at the end, because there's a lot of activities that go into preparing to do software testing. So when you look at agile development, if you remember, the stages were reordered, and software testing was the second phase after requirements. This diagram here sort of illustrates the different steps of software testing. So there's two goals for software testing. There's verification that the specifications are met by the product, and then there's validation that the customer's needs and expectations are met by the product, right? So those things are slightly different goals, but they're all checking that the product meets some specification, whether it's the design specification or whether it's the customer's expectations, right? So if both the verification and the validation don't pass, technically the project will fail. If you remember at the beginning, I said I didn't understand how software projects could fail. Usually they fail not because the product didn't meet the specification, but because the product did not meet the customer's needs, right? So the product meets everything that was said in the design, but the customer doesn't like it. That's a failed project. So software testing is very important. Usually consists of a number of layers, the different layers of software testing. Starting from the top, this is usually think of the diagram as a bit upside down, right? So unit tests are the lowest level of testing, or should I say, is the first testing that developers would write. Integration tests are run when you have the system as a whole. So unit tests are for testing the individual small components. Integration tests are for testing groups of components. A system test is when it's all together. There's a few people leaving and joining. A system test is when it's all together and you're potentially integrating with other external systems, and you want to check to make sure that it's all hanging together. And an acceptance test. Yes, I'm still here. I think there's been a problem. Okay, so it looks like there's a problem. Yes, I can. Okay, great. So let's carry on. I don't know what's happened to GDG Accra. Maybe they can refresh their browser. Okay, so and then the last type of test is acceptance test. Once the system has been verified as functional, then the users or representatives will test the software as part of acceptance testing. So these are usually the layers of testing. Another way of looking at testing is what we refer to as a V model, and basically this shows how the different types of tests validate the different types of artifacts that get created at requirements time, at design time, at detailed design, at implementation, right? So as you can see, if you start from the top, requirements analysis, where you're creating your requirement specifications, those are verified by systems testing. So when you write your system test plan, you write them to verify your requirements that you gathered at the beginning. When you do integration testing, you are verifying the high level design, right? So when you created a design, you probably would have decided that certain components interact with certain components in a certain way. integration testing will verify that. Then obviously your unit testing is where you got your low-level detail design. You've decided what your classes are going to be called, how many methods, how many attributes are going to have. The unit testing will verify that that actually happened, right? So you realize that the V model gives you another view of how do you actually check that all the different things you created have actually been created properly and are meeting their required function. And obviously at the bottom is implementation, and that's how they all come together. One thing that's worth doing is comparing testing in the waterfall development approach to testing in the agile approach. So as you can see, in the waterfall approach, you have the sequence of events or activities with test at the very end, right? So you got one phase where you do testing. If for any reason you run out of time by the time you get to this phase is the one that usually gets cut, because all the other ones take as long as they take. But testing can be squished, right? The difference with Agile is that because Agile is broken down into many more iterations, you get many more chances to test and validate your software. So as you can see in the first box, you go analysis, plan, design, build, test. You go in iterations before you deliver a small chunk of software. Then you have another box, which is another iteration. So you get many, many opportunities to do it, which means that you're building the software into the product. You're not testing it at the end, right? And that's why Agile software you built using Agile usually comes out at a higher quality with less defects, because a lot more testing is done. It doesn't mean that the people who build Agile software are better than the people who build software using a traditional approach. It's just the approach allows you more opportunities to get rid of issues and defects than the traditional approach gives you. So you can see things can happen, requirements can change, customers can change, technology can change, and you still got a chance to sorry about that. Okay, so that's the comparison between Agile testing and hold on a minute, sorry. Right, can you all hear me? Okay, good. So let's carry on. Why don't you call that?
Hello?
Yeah.
Mommy, did you end it?
Okay, so the next slide is a comparison between traditional and agile testing. Can you all hear me? Usually when my house phone rings, the line goes. Okay, brilliant. Okay, great. I saw that. Right, okay. So the next slide is a comparison between testing in an agile, testing in traditional software development versus testing in agile software development. So in traditional software development, the focus really is on finding bugs, right? So you realize that there's a little bit of unit testing at the bottom. In the middle, you have automated testing. And then at the top, you have a big swath of manual testing through the UI. The goal is find as many bugs as you can so we can fix them before we go live. Whereas in agile testing, the focus is preventing bugs, right? So as you can see, a lot more time gets dedicated to writing unit tests. About the same amount of time gets dedicated to writing acceptance tests. And by the time you get to the end of the project, any UI test you're doing is just exploratory to try and catch some edge cases, as opposed to spending a ton of time writing manual tests to prove that there's bugs in your software, right? So the goal in agile testing is to prevent bugs, is to build quality in, whereas the goal in traditional testing is to find bugs. What usually happens is testers in traditional testing are almost working against the developers, right? Because they want to prove that there's bugs in the code. In agile space, testers are working with the developers to try and prevent the bugs from growing in the first place. So it's a totally different mindset, right? It's a totally different set of problems, and it's a totally different way of working. It takes time to get used to that way of working, but when you get there, it is much, much better as an outcome than it is in traditional testing. Can you still hear me? Great. Okay, so let's carry on. Awesome. Another way of looking at it is the cost of fixing bugs. So it's been proven that, you know, the earlier you find bugs in a software development process, the lower the cost to fix it. So if you think about it, right, bugs can appear anywhere in the software process. The bugs don't only appear in the software code, right? So if I, as a customer, I said I wanted a feature X, right, or a feature A, but you thought I wanted a feature B, right? So you wrote down that I want feature B. At that point in the requirements document, you just introduced a bug, right? If you catch that bug there, it is as simple as erasing or tearing the page and writing a new page in the software document. Not a loss is lost. If you don't catch it there and you catch it in design, yes, you have to redo some parts of the design and maybe you're going to write some more documents, but that's about it. Once you develop it into the code, then the cost is almost 3 times. If that code leaves the development phase and gets into the testing phase, then a lot more people are spending time finding the same bug. Now you have to come back and redevelop it, redesign it, and document it again. So the earlier you catch the bugs, the cheaper they become. And this is why agile testing makes more sense, because you are trying to prevent the bug in the first place. You're not waiting for the bug to get to testing before you're finding it. Right? So that's another way of looking at it. So that's a quick overview of software testing and how it sort of fits into the picture. So in summary, learning software development involves a lot more than just learning a programming language. And I've gone through some of the other things that you need to be thinking about when you're learning a programming language. Obviously, you can learn a language first and learn all those things after, but you have to have an appreciation for them to become a good software developer. I mean, I have worked with people who don't have an appreciation for those things. It doesn't make them bad developers, but it just makes them inefficient, right? So you should aspire, once you've picked your language and you're confident with it, to spread your knowledge a little bit more and understand all the different, facets of software development. The problem we all have is that we don't have time, right? We're all quite busy. So if you didn't, if you didn't spend 3 years in university or wherever learning computer science, then you have to make time, in your busy schedule to learn software development, and that's difficult. The other approach, or the other problem, is motivation. I mean, why would you want to spend evenings and weekends, coding and trying to learn some language when you could be at the bar drinking some cold Guinness or some club beer, right? So motivation is also a big problem. But the way I recommend for people to learn programming is like how you would learn anything else, like a martial arts, right? Find an interesting problem to solve, something that motivates you. the best things are problems that you have, right? Let's say you have a problem, you want to do something and there's no software in the App Store to do it. Then choose a language that can help you solve that problem and learn the fundamental language features, right? So I remember I said at the beginning, things like data types, loops, conditionals, functions, error handling. Every language has those, right? If you list those on a piece of paper by your desk and you learn them in that order, I mean, that's all you need. I mean, that's all there is to programming. Obviously, once you know the fundamentals, then it's like building a house, right? You can arrange the blocks so many different ways to build so many different types of houses, but the concepts are the same. Then the key thing is to practice, right? You have to, like anything else, like a martial art, you have to practice and practice and practice to make any progress and become an expert. But then the main thing is, if what you're doing is not fun, if it's boring, if it's tedious, then you won't be able to learn. So make sure you're having fun. The best way is to make sure you pair up with different people, you share your ideas with people, you hang out at places where developers congregate, you go to idea pitch sessions, join the community, because that is how you will enjoy and have fun doing this, and obviously learn it as you go along. There is quite a few online resources, a lot of them free. The first two are paid intensive courses in the UK, so probably not applicable to yourselves, but all the other ones are either free or very, very affordable. So there's tons and tons and tons of resources out there, but there's nothing like actually pairing up with another person and learning together. So I think, learning as part of a community is probably the best way to learn software development. And with that, we come to the end of the presentation. So I believe that the floor is open for questions now. I don't know how you want to moderate this. Doris, over to you.
I don't know, but I think Doris is out, or her mic is misbehaving as well. So I think.
Does anybody have any questions?
Yes. I think even though you've covered some of these things, I think.
Okay, I can hear you though. So if you have any questions. So I think. Does anybody have any questions?
So I'll just drop the question. What are some of the particular challenges involved in learning to program? You've done this basically, but I think I wanted to maybe delve a little bit deeper in some of the challenges involved in learning to program, apart from the notion that it's scary and it's tedious and all that.
Okay, so I mean, I think like learning to learn anything new, there has to be a purpose, right? There has to be a reason why you want to learn it, because I mean, in today's society, there's so many things competing for your time. So that's the first thing. Why do you want to learn it, right? And then once you're convinced that the why is important to you, you need to pick a language that you can easily learn. Learning on your own, like I said, is quite difficult. So if you can partner with somebody, if you can find somebody in the community who also wants to learn the same language, working together or pairing, which is how we describe it, makes it more fun, right? If for instance you're not doing it because your boss says you should do it, right? It is very difficult to motivate yourself, right? So the first thing is find a problem to solve, the why. The why is very important. Then figure out which language you're going to use, the what, right? And then find a partner, find somebody that you can bounce ideas off, and then try it, right? Start small, solve very small problems. I mean, after the session, I'll give Doris some resources to share with you. There's a lot of coding competitions online where you can just participate and try and solve problems, right? That way, you know, obviously we're all quite competitive, so the competition helps you get motivated. But the key thing is finding a problem that you will stick with and solve. It doesn't have to be a big problem. Don't try and build a spacecraft because you won't do it. Pick on a small problem, and every time you achieve a milestone, you will be spurred on to carry on learning. If you hit a roadblock, chances are that you're going to stop it and move on, right? So pick small problems and then practice.
Okay, thank
Any
you.
other questions?
I think I'd like to read some of the questions in the chat, the live chat that have been posted. Andrew is asking, have you ever seen Agile working in an actual work environment? Because I have always seen only Agile Waterfall.
Okay, so I'll repeat the question. Have you ever seen Agile work in a work environment? Because I've only seen Agile Waterfall. So that's a very, very good question. It's a very valid question. So I currently manage a number of software development teams. The teams are responsible for building all the websites that the company that I work for have. I also manage the team that build the mobile apps, right? So the Android apps, so the iOS apps, and you know, all my teams. I wouldn't say they're mature agile teams, right? But they're definitely on the journey to agile maturity. What does that mean? It means that one, rather than doing long, we work in 2-week iterations, right? So every 2 weeks we deliver some software, right? We show our users some software and they can give us feedback. That's one of the key principles of Agile, right? Early and iterative development. We also practice things like pair programming. We do things like test-driven development. We practice DevOps techniques. So we do things like continuous integration, continuous deployment. We do, I mean, so there's techniques that we use. Like, for instance, we have daily stand-ups. So every day the team get together to discuss what they've done the day before, what they're planning to do today, and if there's any blockers. We have a product owner or like a product manager who's responsible for the product. Their job is to prioritize a list of features that we're going to be working on in a particular iteration. You know, so these are all techniques and ceremonies and approaches that the agile ecosystem recommend that teams should do. It doesn't mean that, you know, when you do those things you're agile. I mean, agile is more than just the things that you do. Agile is also a culture, right? You have to build a culture where people are not scared to fail. You have to build a culture where people hold themselves to high standards. You have to build a culture where there's mutual respect. You have to build a culture where people understand the goal of the company and everybody is proud and enthused to work, you know, for you. So Agile is a bit of a beast, right? It means different things to different people. I haven't worked in an environment where they are doing or they're 100% mature in Agile, right? Everywhere I've worked, you know, they do certain things very well and they do some things very badly, right? So I don't think you'll come across, at least I haven't come across it yet, but I have worked in teams that are trying, and I think the least you can do is to, first of all, understand what the Agile space is all about, and then pick some of the techniques that they recommend and try them out. Some will work for you, some might not work for you. I don't think Agile is for everybody. I don't think Agile solves all problems, but I think Agile will make you better than you currently are.
Oh, okay, that's great. Doris is also asking, you to walk us through a typical day in the life of a developer or as a developer. In the life of a developer. In the life of a developer.
Okay, so this is there's a question that says, walk us through a typical day as a developer. This will be our last question. Okay. So this is there's a question. Okay, so let's see. Right. So a typical day in the life of a developer. All right, that's a good question. I mean, I'll use my teams as an example, right? So the day will usually start. We start, let's say at 9:30 with a stand up, right? So the whole team will come together, and the format of a stand up, right, or it's called a daily scrum or daily stand up, is that you want to know as a team where you're at with delivering your commitment for that particular iteration. So we work in 2-week iterations, right? Or 10 days, right? So every day of that 10 days, we come together first thing at 9:30 when we come in. We go around, maybe it's a team of 5 or 7, we go around and say, right, what have you worked on? Have you got any blockers? Is anything stopping you from doing what you plan to do today? What did you work on the day before? And then, we use what you call a Kanban board. It's just a board with columns that, have a status at the top. So not started, in progress, review, testing, done, right? So the idea is that each person pulls stories from left to right, right? So if there's nothing in a right column that you're working on, then you go to the leftmost column and try and pull something that you can work on. Usually we encourage developers to pair. So rather than you working on the thing on your own, you would pair with somebody. You discuss it, you take turns at writing the code while somebody else is reviewing it. If it's a simple problem, you can take it on yourself. You spend about 45 minutes or an hour working on it, because really your concentration only lasts for about 45 minutes. So if you picture every 45 minutes you're taking a break, or you're having a chat, or you're pairing, or you're swapping pairs, that will bring you to around lunchtime. About 3 sessions of that will bring you to around lunchtime. You sort of take a break, take lunch, come back. There are various meetings that happen during the day. You have architecture design sessions where somebody will be walking the team through, a design decision they've made. You could have meetups or brown bag sessions where somebody's presenting on a topic, either some new technology we're going to use, or something that they've learned over the weekend they want to share. So it's quite a varied day. You won't normally spend every day of the whole week just coding, right? There's a whole number of different activities that happen alongside actually writing the code. I mean, if we're trying to deliver something urgently, then obviously there's less disruptions and we all focus. But generally, there's a mixture of coding, hardcore coding, and a bit of socializing and a bit of learning as well. And then obviously on the Friday we all go out for a few beers, get drunk, and then spend Saturday recovering. Answers your question.
Yeah, great. Thank you very much. Thank you very much for the answer. Also, soon we come to the end of this Hangout, this tutorial 101 series. Officially, on behalf of GDG Accra, we say a big thank you, Frank Amankwa, for taking the time off to do this. We hope by this, many beginners have had their questions answered. This is the first of the 101 series. This is a mix of online and offline tutorials or meetups to get beginners on track, up to date, and confident enough to take the world. Thank you all for making it. See you next time. And thank you, Frank Amankwa, once again.
You're welcome.